All right, so I am Raicu. I am the new faculty member that was hired just this year, so I've been on the job for about a month now, although it feels like I've been here for a long time. My schedule's full, and I guess mid-August, but yes, close to 2 months. But it feels like I've been here already for a long time because I've already gotten to know a lot of people here and a lot of students, and I'm busier than ever. All right, so what I want to talk to you about today. So, uh, there's three main things up here. I've got many-core computing, exascale computing, and cloud computing, and I'm going to talk to you what they have in common with each other, and perhaps what I think are some of the interesting things that we can do in from a research perspective to make progress in these areas. Okay, so let me first tell you a little bit about each of these three areas. So many-core computing. What we have is we have the number of cores per processor that is increasing at an exponential rate. We're currently somewhere in this area of about 10 cores per processor. We used to be at 1 core per processor. I'm sure you all remember your computers that only had one core in each processor. That was about 80 years ago, right? I'm not going to get into too many details of what happened, why 20, 30 years of processor design all of a sudden changed 8 years ago, right? Because for a long time, we just went megahertz, megahertz, gigahertz, gigahertz, and we just kept increasing, right? Every year we'd get double the processor speed, and everybody was happy. And around 2000, 2003, something happened, and they started going, well, can't make processors faster, we're going to add more cores. So today, we're somewhere in the landscape of about 10 cores. This is kind of the commodity chips, things like AMD and Intel, the things you buy in like a Best Buy. If you start going into some of the more proprietary architectures, there's maybe up to about 100 cores. There's different designs. And if you start going to GPUs, which again, many people have on their machines for gaming and all that kind of stuff, you're talking about, again, hundreds of cores. Now, there's a big gap here between, how do you program these things, right? So these are the easiest to program because that's what we've had for the longest time, and then these are obviously changing the programming paradigm. The claim is that, in the next decade, we're going to have about 1,000 cores that are kind of commodity general purpose cores. And it's possible that the GPUs will be merged with your generic cores. So basically, these 1,000 cores will handle everything from graphics to your general purpose computing. So that's one of the trends that are happening. So what about exascale computing? What is exascale computing? Anybody know? Just out of curiosity. No? How about
More t-shirts.
More t-shirts, okay, yeah. Okay, half a t-shirt if anybody knows what petascale computing is. Petascale? No? All right, so, exascale is referring to the number of operations per second that can be done in a computer system. It refers to essentially the supercomputing of the next decade, right? So basically, by the end of this decade, by 2018, 2019, people say they will be able to do exascale levels of computing. It's 10 to the 18th, I believe, number of computations per second. What that means is that we'll roughly have the equivalent of, the brain capacity of a human being, for example, that has about that much capacity. Okay, so in theory, we should be able to simulate the human brain with an exascale computer. Now, what does this really mean? It means that if you actually look at, I've got another graph here. I should have put this one first, actually. What we actually see is that the biggest machines, this is basically in time and logarithmic scale, you see an exponential increase in terms of capacity. We're currently here around petascales. We're 1 petaflop, 2 petaflops. and then a decade will be up here, which is about 1 exaflop. And if you notice, a decade ago we were probably at teraflops, and then a decade before we were about a gigaflop, right? So these numbers are, kind of, they're very hard numbers. They're set in stone, and they're coming from, they used to come from the fact that we were increasing speed of the processor. Now they're coming because of this graph of increasing the number of cores from the many-core computing era. Okay, so what we're doing is we're going from today's biggest computers that have tens of thousands of nodes and maybe hundreds of thousands of processors. We're going to go to millions of nodes and billions of processors. Okay, so this will have a lot of implications in different areas, which I'm going to talk about, and a lot of hard challenges. Really, I mean, it could be to the point where if we don't solve all of them, it'll be a showstopper, and it'll be just a heater, right? You'll get a big machine that will just produce heat and won't really do anything. Okay, it's happened in the past with other architectures that were built. All right, cloud computing. Supercomputing has been around for 30 years, 20, 30 years, probably since at least the 80s, maybe earlier. Grid computing is another paradigm that was from the 90s. Cloud computing is the newest member to the distributed systems family, which is only a few years old. If you go to Google, you'll see that late 2007 was the first time it appeared on anybody's roadmap in terms of, kind of keyword search. All right, so cloud computing is essentially trying to bring distributed systems to the average, person, to small businesses, kind of making computing a utility, right? Making you not have to buy infrastructure anymore, just rent it, not have to run your own infrastructure, but be able to just kind of outsource your needs. So if you look at Amazon, which is one of the biggest cloud computing infrastructure as a service vendors, when I say infrastructure as a service, they're the ones who rent the computing. What you have is you've got about 40,000 servers. This is kind of speculation. It's from a report I read, but it's probably, give or take some 25, 50% right? 40,000 servers, a few 100,000 cores. Took about 100 million to build, and it costs about 10 million, 12 million to power. This is actually very similar to a supercomputer setup, right? The Blue Gene or Argonne has 40,000 servers, 160,000 cores, costs 200-some million to build. You've got about the same scales. And at the rate that cloud computing is actually taking off, it's very possible that cloud computing will see the same scales that exascale will see. Okay, millions of nodes and billions of cores. Okay, so the thing is that the exascale and cloud computing have a lot in common from this perspective, that the scales that they'll see are likely going to be quite common. Okay, so what are some of the challenges? So I've highlighted 4 different areas. First one is power efficiency. I'm not going to dive too much into this because it's not my area of research, but just so you know that power will be a big thing that needs to be solved in terms of making the processors more efficient, being able to cool them, for example, the density of these systems. The lower the power, the better. So there's a lot of emphasis actually in the community of trying to come up with better hardware designs that are more efficient. For example, the RISC architectures are actually making a comeback from the mobile devices, but actually into, think of the iPad, right? It doesn't have the traditional processor, but yet it's used as a traditional computer almost, right? I mean, I can do everything I can do on this. I could almost do everything that I do on a laptop, but yet it doesn't have the hungry processors that the laptop generally has. And therefore, I can actually charge it only once a week, right? I don't have to charge it every day. Okay. Next one, programming models. There's a lot of stuff that actually needs to change here because we're going from a world of single-threaded computing that we've done, that 99% of the programmers in the world have done since they've been programming, And we're going from, even in the supercomputing space, from maybe thousands of cores or processors up to in the hundreds of thousands and millions and billions in the near future. So there's a lot of work that needs to happen here, from parallelizing code automatically, perhaps looking at different models other than threads or MPI. Do you implement features in languages or middleware, et cetera? Third one is bottlenecks in the system. As you scale up these systems and technology evolves, the bottlenecks shift. Dr. San mentioned the memory bottleneck, right? The memory wall, as it was not a problem 20, 30 years ago, but it is now. The exact same thing is happening in these large systems that what used to be the scarce resource, the CPU, is not anymore the scarce resource. It's now the scarce resource is actually the the storage infrastructure, for example, right? So at least in these exascale systems and potentially even the cloud computing systems, the storage will likely make or break one of these big systems, because that's how the machine becomes reliable, because it can save state. That's how the applications run. That's how the applications, so the storage is in the middle of the fast path, essentially. It is not just this place you keep things and so forth. There's, memory controller and the memory hierarchy. That's very important from the many core computing, the model that we have had so far, where all the cores are identical. It's a homogeneous system, and you've got equal access costs from any one core to the memory. It won't work when you have 1,000 cores on the system. And finally, the fourth one is reliability. How do you actually keep 1 million nodes up and running with high reliability, or 1 billion cores? So in HPC, it's actually a very big problem. Mean time to failure of current systems is on the order of days, right? And it'll likely take that mean time to failure down to hours in the next decade. So I think I'll wrap up there, but essentially just keep in mind that there's actually a big shift towards this large-scale computing. Industry is pushing cloud computing. The government labs and academia is pushing on exascale computing. Many core computing is also being driven by industry, and there's a big effort in terms of pushing parallel computing from a niche market to the general educational population, because in essence there will be no more free rides where you just keep getting faster processors to speed up your algorithms anymore. All right, any questions? We got about 1 minute before we shift to the next speaker.